on post-quantum cryptography. While Varun sets up, talk is on the post-quantum anonymity of Kyber, and this is one of the two best paper award winners. It's by Varun Maram and Keita Jagawa, and Varun will be giving the talk. So I will let Varun have the floor.
Can you hear me? Okay. Yeah, so welcome everyone. I guess, let me just check, yeah. I guess I have the misfortune to talk about security proofs at 9 a.m. in the morning, so please bear with me. So I'll try to keep things at a very high level. So I'll be talking about post-quantum anonymity of Kyber, but in hindsight, the title of my talk should actually have been post-quantum in CCA security and anonymity of Kyber, as will be apparent in my talk. So this is joint work with Keita Kusagawa. So to get some context behind our work, we need to go back in time when the NIST PQC standardization process was in its third round with 4 finalists and 5 alternate candidates in the public key encryption category. By the way, spoiler alert, Kyber was eventually chosen as a winner. And as specified by NIST, a main criteria of evaluation for these schemes was on how well they achieved so-called in-CCA security. However, a couple of recent works published last year, they argued that in-CCA security is often not sufficient for some modern applications. For example, applications such as anonymous cryptocurrencies like Zcash, digital auctions, privacy-preserving credential systems, etc., not only require in-CCA security of their underlying primitives, but also require properties such as anonymity. It's also not a coincidence that Keita and we were involved in these works. And just a quick recap. So in CCA security, roughly speaking, guarantees that when Alice encrypts her message using Bob's public key, then the message does not reveal anything, the ciphertext does not reveal anything about the message to Eve. On the other hand, anonymity, or more formally ANO-CCA security as formalized by Bellary et al., it guarantees that the same ciphertext does not leak the public key used by Alice to encrypt her message. That is, the identity of the receiver is hidden from Eve. So after arguing about the importance of anonymity, so these two works, they set their sights on the NIST PQC third round candidates to see whether they satisfied this notion of ANO-CCA security as well. So for now, we'll be focusing on the 4 finalists. Now, syntactically, these 4 candidates are chems, key encapsulation mechanisms. And to construct their chems, they employ a generic technique known as the Fujisaki-Okamoto transformation, or FO transformation for short. So in such a transformation, they first construct a weakly secure base PKE scheme, and then compose that with a couple of hash functions to construct the final chem. Now, here's a concrete example of such a transformation in the literature, so don't be overwhelmed by the pseudocode. So essentially, the way the chem works is that it encapsulates its keys by first randomly sampling a message from the message space of the base PKE scheme, and then encrypt the message in a deterministic fashion where the random coins are just a hash of the message. And then finally, the message and the ciphertext are hashed to generate the final encapsulated key. And decapsulation proceeds in a straightforward fashion, but where you do an additional re-encryption check. That is, you decrypt your input ciphertext, and then you re-encrypt in a deterministic fashion and check if the ciphertexts match. And one important thing to note here, so this transformation is called FO not bot. So the reason you have the superscript not bot is because, let's say the re-encryption check fails. When it fails, so instead of returning an error, instead of outputting a special error symbol, you output a pseudo-random value here, which is a hash of a secret value S that you sample in the key generation and the input ciphertext. So now this aspect of rejecting invalid ciphertext during decapsulation will play a very important role in the rest of my talk. Okay, so now coming back to our transformation, so if you use this standard FO not bot transformation from the literature to construct your chem, then Jiang et al. They showed that if your base PKE scheme satisfies this weak notion of one-wayness or in-CP security, and if your hash functions, they behave as so-called quantum random oracles. So quantum random oracles means that you give the adversary the ability to query the hash function on a superposition of inputs. Then your final chem will satisfy the strong notion of in-CC security. And subsequently, Grubbs et al. And Kusagawa, they showed that if your base PKE scheme satisfies some additional mild properties related to anonymity, so I won't go into details what these are, then your final chem will also satisfy this notion of ANO CC security as well. So just a minor point. So recall that in when I was talking about this Alice and Bob scenario, we were strictly talking about NOCC security of a public key encryption scheme. But here we're talking about NOCC security of a chem. So what it means, it's not very important, but it was formalized by these works. But what's important is that an anonymous chem also gives you anonymous public key encryption scheme when you compose with an appropriate DEM. So for now, we can just restrict our attention to anonymous chems. Okay, so now then these works are first focused on classic McAleese. So classic McAleese, it turns out, it uses not exactly the FO not-bot transform from the literature, but a slight variant of it where in your ciphertext you have some additional hash. But rest assured, so Kusagawa was able to extend the anonymity properties of this FO transform to the transform used by classic McAleese while accounting for this additional hash to show that, yes, classic McAleese does gives you anonymity in this post-quantum setting. Coming to NTRU, so again, recall that in our standard FO hash, FO transform, you hash both the message and the ciphertext. However, NTRU, it only hashes the message. It does not hash the ciphertext. So this transform used by NTRU is equivalent to another transform in the literature, which is known as FO not-bot with a subscript M. And Kusagawa was able to extend the anonymity properties of this FO not-bot transform. And he was able to show that, yes, even this transform with the subscript M gives you anonymity in the post-quantum setting. And coming to Kyber and Saber, this is where things get more interesting. So again, recall that in our FO transform, you hash both the message and the ciphertext to get your key. But Kyber and Saber, they use a different transform where what you do is you first hash the message and hash the ciphertext separately, and then you hash those hashes to get your key. So there is a lot of hashing going on here. And as argued by Grubbs et al. And Kusagawa, they said that this nested hashing of ciphertext, not only does it create problems when you want to formally establish the anonymity of these two candidates, but it also creates problems when you also want to formally prove even in CCA security of the schemes in this quantum random oracle model. And now fast forward to last year, when NIST chose Kyber as its sole PQC standard for public key encryption. At the same time, the Kyber team, they did acknowledge that this thing of the hashing of the ciphertext, it does complicate any attempts to prove security in the QROM for Kyber. And hence they proposed, for the mailing list, they started this discussion about proposal to go back to one of the standard FO transforms for the chem construction instead of doing all these weird internal hashing. But of course, one disadvantage of this proposal is that, so just changing your underlying FO transform is not a trivial change. It again probably would require an extra round of security evaluations and things like that. So that's why, and I'm not even considering additional patent issues that might arise if you're changing your underlying FO transform. So this is again, maybe not too ideal. So this brings us to the contributions of this work. So here we analyzed the version of Kyber as it stands currently with this additional hashing of ciphertexts, among other things. And then we concretely gave a concrete and tight proof of NCC security for this weird version of Kyber in the QROM. Informally, our security theorem looks like this. So essentially what this says is that the NCC security of Kyber is can be tightly related to the NCC security of the standard FO chems in the literature, but we also incur an additional term in our bounds, which has to do with collisions in this nested hashing of ciphertext. So maybe we'll talk about this near the end of my talk, hopefully. And this approach to formally prove NCC security of Kyber also allowed us to formally establish post-quantum anonymity of Kyber as well, and the PK schemes that you can derive from them. And the final thing we're pointing out is our positive results for Kyber do also extend to Saber because of the fact that both schemes essentially use the same type of transform. So in the rest of my talk, I'll try to give a high-level overview of our approach. So on this left is you have a standard, I'll do this by first describing a simpler and maybe an alternative approach to prove NCC security of Kyber. And then I will contrast the simple approach with the approach that we took in our work in the end. So on the left is yet another standard FO transform in the literature, but here you have a subscript bot. So here for invalid ciphertext, you do return a special error symbol bot. That's why you have a subscript here. This is in contrast to the F4 not bot M, where you return a pseudo-random value. So now think of this transform as your favorite piece of chocolate. So in this presentation, I chose the lint dark chocolate. Now this analogy will be clear later on. And now on the right, you have a simplified version of the F4 transform that is used by Kyber. That is with this additional hashing of ciphertext that you do in this encapsulation. This is simplified because I'm not accounting some additional hashing that is going on, because it's not relevant for this overview. But rest assured, our analysis in the paper does account for this additional hashing as well. Now think of this Kyber as a fully wrapped lint chocolate. Lint because I come from Switzerland, but this talk is not sponsored by Lint, by the way. I'm just putting it out there. Now the reason I chose this analogy is because Kyber can be seen as a scheme which is obtained by starting with a base chem, which is obtained by this F4 transform, and then you apply an appropriate wrapper transformation, which takes this chem to this final product. So the way this wrapper transformation works is as follows. So if you start with key generation, then let's say this dark chocolate outputs a public key and a secret key. Then what the wrapper does is it samples a secret value S, which will be used for implicit rejection and for rejection of invalid ciphertext. And then you include that in your secret key, and this will be your final secret key of your fully wrapped chocolate. Coming to encapsulation, when this chocolate outputs a ciphertext and this key K bar, so what the wrapper does is it uses two additional independent hash functions, H and H prime, and then for its final key, it hashes the key K prime along with a nested hash of the ciphertext. So this is exactly what's happening in this encap procedure in Kyber as well. And again, decap proceeds similarly. So when in decapsulation, when this chocolate outputs key K prime, which is not bought, then it means that the decapsulation was performed on a valid ciphertext. Then the wrapper, it just again does a nested hashing as we have seen just before. But what's important is that if it returns a bot instead, that is the decapsulation was performed on an invalid ciphertext, then the wrapper recognizes this, and then it does this implicit rejection by using this secret key as it sampled at the beginning. That's exactly what's being done in Kyber as well. So to summarize, since you have Kyber to be like a wrapper scheme which wraps around this underlying F4 not bot transform, or F4 bot transform, it's straightforward to reduce in-CC security of Kyber to the in-CC security of these explicitly rejecting F4 bottom transforms in the QROM. So then it appears that the issue is solved, right? Then why did we go into troubles about trying to formally prove in-CC security of Kyber in the first place? There is an issue, and it has to do with our reliance on the in-CC security of these chems in the QROM in the first place. So just to be more specific, if you compare the in-CC security of these F4 bot M transforms with that of its implicitly rejecting F4 not bot M transform here, then it turns out that all the existing security proofs that we have for this variant of the F4 transform are significantly non-tight when you compare with the proofs that we have for these F4 not bot M transforms. So implicit rejection makes it easier to obtain tight proofs of security. So this non-tightness would also extend to Kyber as well. Not only that, but arguably the techniques used to prove the QROM security of this F4 bottom chems, they are quite complicated, and they do not yet allow for formal verification of the proofs. This is again in contrast to the implicit rejection variant, where we do have means to formally verify the proofs as shown by Unruh. And finally, recall that the title of this work was Post-Quantum Anonymity of Kyber. So we are also interested in establishing anonymity of Kyber, but to the best of our knowledge, the post-quantum anonymity properties of these explicitly rejecting chems were not explored in the literature. This is in contrast to the implicit rejection, for which you do have positive anonymity results by these two papers. So since we have all these ideal properties of our implicit rejection chem, the question we ask in our work is that, can we somehow base the in-CC security of Kyber on the in-CC security of these implicit rejection chems instead of this explicit rejection? So let's do that. So let's try to again use the similar wrapper-based approach that we used. So but here, instead of starting with this explicit rejection chem, so instead of starting with the dark chocolate, let's change the flavor a bit and let's start with a caramel chocolate. So the caramel chocolate, it outputs not an error symbol, but it outputs a pseudo-random value. Now it's not hard to see that we can come up with a wrapper, the same wrapper as shown before, which can translate the key generation as seen before, and even the encap as as before as well. Because when you're changing the FO transform, we are not touching these algorithms, but we are only touching the decap. The problem arises when you want to translate the decapsulation procedure instead. Because now, when the caramel chocolate, it outputs a key, K bar. So note that it does not output a special error symbol at all now. So the wrapper does not know what to output, because this key can either be a result of decapsulating a valid ciphertext, that is, it can be a hash of M prime, or it can be the output of an invalid, decapsulating an invalid ciphertext. So the wrapper cannot decide which key is what. So this brings us to the approach we took in our work. So what we did was we started with how invalid ciphertexts are rejected in decapsulation by these two schemes, and then we tweaked them a bit. So we modified the rejection values as shown here. So these are just some nested hashing of the ciphertext. So I will talk, I'll discuss shortly why we chose such weird expressions. So don't be scared by this. In the process, we ended up modifying the underlying transforms as well. So instead of caramel chocolate, now we have a milk chocolate, which rejects like this. And now the reason we chose the specific values is because now it's easy to come up with a wrapper which translates this decapsulation procedure to the new decap procedure. So specifically, when this milk chocolate outputs a key K prime, what the wrapper does is it outputs the simple value, a hash of K prime along with a nested hash of the ciphertext. So the reason this works is because, let's say this K prime is output of a valid decapsulation of a valid ciphertext. So that is, the key is of the form a hash of M prime. So if you replace this K prime with this hash of M prime, this is exactly what's being done in this decap procedure. So that's all right. So the outputs do match. And interestingly, so when you're dealing with an invalid ciphertext, then this K prime is this nested hash of the ciphertext. So where H over line is an independent hash function. So if you replace this K prime with this weird value, this is exactly what's being happening here as well. So again, the values match. And now, because of this observation, it is again easy to reduce the in-CC security of this modified Kyber on the in-CC security of this modified FO bottom transform. But again, there's a problem, because we are not really interested in in-CC security of some modified Kyber, right? We want to prove in-CC security of the original Kyber. And also, we are not sure, we do have tight proofs of security for this FO bottom transform, but we don't know what this modification will give you. Fortunately, in our work, we also show that we also do these modifications in such a way so that the in-CC security of these resulting schemes are tightly related to their in-CC security of their unmodified original counterparts in a computational sense. So hence, all these observations then give you that, yes, you can in fact base in-CC security of Kyber on the in-CC security of the unmodified FO bottom transforms, for which we do have tight proofs of security in the literature. So I don't have much time remaining, I guess. So I'll quickly go over how we establish anonymity as well. So with this in-CC security result in hand, one might expect that we can also prove anonymity in the straightforward fashion by using anonymity of the underlying FO bottom chems. But in our approach, we took an indirect approach where we in fact showed that Kyber satisfies a strong notion of security called strong pseudo-randomness. Essentially, what it means is that in-CC security, recall that the keys, encapsulated keys, are indistinguishable from random bit strings, but in strong pseudo-randomness, even the ciphertexts are indistinguishable from random bit strings. So using wrapper-based approach, we showed strong pseudo-randomness of Kyber, which straightforwardly implies its anonymity. I will try to conclude my talk by discussing some open problems and some approaches. So, okay, so this basically says that how we end up with the collision resistance term. So yeah, this is the collision resistance term that we relied on. But this is not the only approach to prove in-CC security of Kyber. We can also use a recent result of Zandri, which essentially shows that this weird key derivation in Kyber is indifferentiable from a normal key derivation that you use in standard FO transforms. So that means that if you try to use, again, a similar wrapper-based approach, then instead of collision resistance, you incur an additive term, which has to do with this indifferentiability loss when you replace this weird key derivation with normal hashing. And just last year, there was another attempt to concretely prove in-CC security of Kyber, where on a high level, they worked with random permutations, whatever, and that's why they incurred this additive term. If you compare our theorem with these bounds, So we observe that, so here recall that Q is the number of hash queries that you allow the adversary to make. And it turns out that if you do some back of the envelope calculations, then our bound strictly allows for more number of hash queries for which the bounds do remain meaningful. And another nice thing is that, so these two techniques, they, on a very high level, they rely on on a very powerful technique by Zandri known as a compressed oracle technique in the QROM setting. In contrast to their technique, so we rely on arguably simpler proof techniques to be specifically recalled on something known as a one-way to hiding lemma by Ambinus et al. So it's not very important, but what's nice about this is that this simple lemma, it does allow for formal verification of proofs as shown by Unruh. So this brings us to my first open problem, namely formal verification, because just saying that there exists a framework in the literature which can formally verify proofs for you is not enough. Someone needs to actually sit down and tailor the framework to suit our concrete proof of security in order to formally verify it, thereby providing more confidence in the niche standard. And another open question is that, are our bounds optimal? Because so one might try to come up with a tighter proof of NCC security, which does not have to go to this route of collision resistance, thereby avoiding this term and strictly allowing for more number of hash queries from the adversary. On the flip side of coin, can someone show that this reliance on collision resistance is indeed necessary by coming up with a matching attack where you can attack NCC security by exploiting collisions in your nested hashing of ciphertext? With this, I conclude my talk, and thanks for your attention, and I'm happy to take any questions.
Thank you very much. There's time for maybe one question. Maybe the next speaker can come set up otherwise. Oh, okay, great. All right, let's thank Varun again. Great talk. Okay, so our next speaker is online. And the next talk is QCCA secure generic transformations in the quantum random oracle model. The paper is by Tianxu Shan, Zhengxia Ge, and Rui Zhu, if I've pronounced that correctly. And Tianxu will be giving the talk, and I will give the floor over.
Then can you hear me?
Yes, we hear you fine. Thank you.
May we get started? Okay. Just for a second. Fine. I'm Tianxu Shan from CES, and today I would like to introduce a paper entitled with QCC secure generic transformations in the quantum random oracle model. And this is a joint work with Zhangxia Ge and Rui Xue. And this presentation consists of 4 parts. And first of all, we'll go over the definition of the QCC security and compress the standard oracle. Here we abbreviate public key encryption scheme as PKE and quantum random oracle as QROM. Given a PKE, for any adversary in an ND-QCC security game in the QROM, the adversary can make random oracle queries and decryption queries in superposition. And it also make one challenge query M0 and 1, and one of the messages B is encrypted to be the challenge ciphertext, and the adversary finally output a bit B prime. If for any efficient quantum adversary, its output B prime is B with probability at most 1/2 plus a negligible quantity. Then the PKE is ND-QCC secure in the QROM. And the compressed standard oracle, and CSTO for short, is applied to simulate quantum random oracle perfectly. It records random molecule queries in the database state. And this shows how CSTO operates. After reviewing the definition of IND QCC security and the CSTO, let's look at the result of this paper. And the result is summarized as 3 points. Firstly, from the result scheme of Apple and the React transformation, the common feature of these two schemes is that the decryption process contains the re-encryption process as highlighted in red font. And this property is captured, and this type of schemes is formalized as Oracle masked scheme, and OM scheme for short. Next, for OM schemes in their QCC proof in the QROM, an upper bound of the error caused by the simulation of the decryption oracle is also given. And specifically, as shown in the area circled by the dashed line, the quantum random oracle is simulated by CSTO, and random oracle queries are recorded in the database state. Then in Game G2, the only change is the decryption oracle is simulated by searching in the database state, and an upper bound of these two games is given. And for example, in the QCC proof of Apple, if the underlying PKE is gamma squared, then the probability difference of these two games is upper bounded by 5 over the square root of 2 to the gamma. As the last point, we repeated the QCC proof of Apple badge engine and provide QCC proofs of transformation, Apple, React, and T subs H with concrete security bounds. And the table in the bottom up lists the security assumption of the underlying PKE, the security of the achieved ones, as well as additional requirements for those 3 transformations respectively. And after the introduction of the result, let's turn our attention back to the motivation of this work. To begin with, we review the classical security of Apple, and it combines a one-way secure PKE and a one-time secure symmetric key encryption scheme into an NDCC secure PKE in the ROM, and this proof is accomplished with 4 games as presented in the bottom of them. On the other hand, as for the research on the post-quantum security of Apple, adversaries are capable of quantum computing, and it is reasonable to assume that they can query random oracles in superposition, and furthermore, in some cases, it could be possible for them to query decryption oracle in superposition. And to those considerations, 2 questions are proposed as shown in the orange area. And specifically, can Apple transform a one-way secure PKE into an NDCCA or even QCCA secure PKE in the QROM? And to answer yes to those 2 questions, QROM proofs are needed. And it is nature to try to lift the ROM proof into the quantum setting. Nevertheless, in the early stage, people didn't know how to simulate quantum random oracle on the fly. And this prevents the challenger in the security games from recording adversaries' random oracle queries, and makes it hard to simulate a decryption oracle without secret keys. And as shown in the bottom half, one solution to this problem is that FO is modified by adding a hash value h prime of delta to the ciphertext. And it was proved that the modified FO transform a one-way secure or an ND-CP secure PKE into an ND-CC secure PKE in the Q row. And after that, the compressed oracle technique provided a way to simulate quantum random oracle on the fly. And in this way, random oracle queries can be recorded in database state without adversaries detecting. And the challenger can perform measurements to database state to get some information on adversaries queries. And this enables to simulate decryption oracle even for quantum queries. And it was also proved that the unmodified FO transform a one-way secure PKE into an ND-QCC secure PKE in the Q row. However, in that proof, 4 games are defined to change the simulation of decryption oracle. And until in game G5, the secret key is not needed. So, but in contrast, in the room proof, that change is more straightforward, and we wonder if Q-room proof can be as simple as room proof. That is to say, can we change the way to simulate decryption oracle in one step and provide an upper bound for this change? And in the last part, I'd like to focus on the details in the proofs of transformations in this paper. And since their proofs are outlined similarly, here we take IFO for instance and analyze 2 points in its proof. The first one is the simulation of decryption oracle. In the QCC proof of FO, random oracle H is simulated with STO, and random oracle queries to H are recorded in the database state. Then in game G2, the decryption oracle is simulated by just by searching the database state. Just follow the way of simulating decryption oracle in the room proof. Note that the resulting scheme of FO is an OM scheme, and with the result of this paper, by the well-spreadness of the underlying PKE implies that the GIN G1 and G2 are indistinguishable for adversaries. And the second point is the simulation of challenging ciphertext C star D star. And in game G3, when generating C star D star, K star and R star are uniformly chosen to replace G of delta star and H of delta star D star. And the adversaries wouldn't find this change if G of delta star and H of delta star D star are uniformly random in its sphere. And to achieve this goal, binary measurement is performed on random oracle queries to test whether query state contains delta star or not. But that's not enough, because the decryption process of G2, which is denoted as U subject T, would disturb the simulation of H of delta star D star. And here we explain this thing with an example. And as shown in the light yellow area, an adversary in game G2 firstly make the challenge query and then query the numerical insuperpopulation. And for any pure state of decryption query that C event C star and D star and delta star can be encrypted to C, U sub xt would entangle this query state with the database state on delta star D star, and this entanglement would disturb the simulation of H of delta star D star. And to handle this situation, before game G3, we add new game G2A, and in this game, the simulation of decryption oracle is changed again, and the decryption process of game G2 and G2A are identical until C star D star is defined. After that, in game G2A, for any decryption decryption query state, unitary standard decompression sub delta star D star is performed on the database state. Then you sub xt, and finally the first step again. By this change, the simulation of H of delta star D star wouldn't be disturbed by the decryption process. And it can be concluded that game G and game G2 are indistinguishable for adversaries, and here's the reason. Unitary standard decompression sub delta star D star almost commutes with U sub xt, and it is indistinguishable to swap the second step with the last step. Then, since standard decompression is an evolution, so these two unitaries are deleted, and the resulting unitary is the decryption process of game G2. And in summary, in this paper, Oracle master scheme is defined to capture the re-encryption property of PKE, and for Apple and React, whose resulting scheme is an ON scheme, we provide QCC proofs for them with concrete security bonds, and that's all. And thank you. Thank you for your attention.
We have a couple of minutes for questions. I have one question. Can you hear me?
Yeah.
The QCCA security bounds, how do they compare to the CCA and the QROM security bounds? Are they looser? Do they match? How do they compare?
Well, let's turn back into the definition of QCC security. We can see that the decryption oracle is permitted the superposition query, and any attack in that breaks the NDCC security would implies attack that breaks the QCC security. And so in another word, we can see that if PKE is the QCC secure, then this PKE is NDCC secure.
Okay. All right. Is there another question? No? All right. Let's thank Tianxiu again.
Okay.
Great. All right. We're a little ahead of schedule, which is good. So our next talk is on a thorough treatment of highly efficient and true instantiations. The work is by Julian Duman, Catherine Hovelmans, Eike Kiltz, Vadim Lubashevsky, Gregor Seiler, and Dominique Unruh. And Julian will be giving the talk.
Yeah. It's 1 or 3, I think. No, nope. Another paper number. PowerPoint or what slide do you use? PDF. I don't know if paper number I can have it. Where was the sent?
Paper from the conference.
Yes, in the acceptance letter, in the acceptance email. Okay. No idea. I don't have any. Do you have access to my email here?
It should be paper number 98.
Thank you. Thank you, Kay.
Sure.
Is this right? Yeah. Okay. Thank you, Kay.
Can help me with the mic?
Yes, so you're supposed to follow this.
Can you hear me?
Put that in your pocket.
Can you hear me? Yeah,
Yes, we're all good in Zoom.
perfect. Then hi, everyone. My name is Julian. I'm a PhD student at Ruhr University Bochum. And today I'm going to present you our work on a thorough treatment of highly efficient entry instantiations. This is joint work with Katrin Hövelmans, Eike Kiltz, Vadim Lubashevsky, Gregor Seiler, and Dominique Unruh. So, oh, it's not presentation mode. Sorry, real quick. Okay. Work. Yeah, perfect. Sorry for that. Okay, so so let's quickly review Entru. So Entru was the really first practical quantum secure lattice-based encryption scheme. And in Entru, we work over a ring, a polynomial ring, with public key is of the form G divided by F, where G and F have small coefficients. And the ciphertext is of the form of a ring element R, randomness multiplied by the public key, and then the message added. And we have an error distribution here called eta. And so Entru is one way under the ring LWE and entry assumption. And very roughly, the entry assumption states that the public key as generated in Entru is computationally indistinguishable from a random ring element. And the ring LWE assumption states that it's difficult to recover the message given the Entru ciphertext where the public key is chosen random. And 3 of the 17 first round lattice list PQC candidates use some variant of Entru. And now I want to talk about an important property of Entru. And it is that of decryption errors. So in the decryption, we multiply the ciphertext by the private key, and then take everything modulo plus minus q and then modulo plus minus 3. And so here we have what I call here the correctness term. And due to that correctness term, we need for correctness that all the coefficients of this term are smaller than q divided by 2 in absolute value. But for an adversarially chosen message, the coefficients can be larger than that. And this is the reason that we only have usually only average case correctness, which means that for an honestly generated message, public key and randomness. And so this is the reason one can't directly obtain a CCA secure KEM, but has to do more work. And in fact, I want to highlight that an adversary forcing decryption errors can leak the secret key. A possible solution for this problem is that one can increase the modulus Q to obtain perfect correctness and then relatively straightforward get a CCA secure KEM. But the effect of doing this is that the entry assumption gets weaker and the compactness of the scheme is also impacted. So the solution that we have is that we apply an error reducing transform first to turn the average case correctness errors into worst case ones. Then apply the well-studied Fujisaki-Okamoto transform to obtain a CCA secure KEM. And the effect of doing this is a smaller modulus Q, which leads to a better security of the entry assumption and a more compact scheme. So this is the overview of our work. We propose 3 entry variants, entry A, B, and C. The first one, entry A, is directly with worst case correctness. And we have 2 error transforming transformations, ACVC, which is size preserving, and one ACVC 0, which is not size preserving. And we analyze those in the random oracle model and the quantum random oracle model. And we properly analyze the worst case correctness, which allows us then to apply the Fujisaki-Okamoto transform to obtain the CCA secure KEMs. As a practical application, when we instantiate the schemes with number theoretic transform friendly rings of this particular form, we obtain a scheme which is 15% more compact, 15-time improvement in the ephemeral round trip time, 35-time faster key generation, 6-time faster key encapsulation, and 9-time faster key decapsulation than the NIST finalist entry HRSS 701. So now let me walk you through how we obtain the final schemes. So let's start here with a generic entry template with average case correctness errors. So this is a generic entry template that we use. In decryption, we sample from the error distribution and generate an F. And if F or G are not invertible, we restart the algorithm. And we have a well-known optimization where we derive F by multiplying 3 times F prime plus 1, which gives a more efficient decryption algorithm. For encryption, we sample from the error distribution R and then multiply the public key by R and add M. And for decryption, we multiply the ciphertext by the private key, take everything modulo plus minus Q, and then modulo plus minus 3. Maybe another thing to highlight is that the scheme is randomness recoverable, which means that given the ciphertext, the public key, and the message, one can recover the randomness used, which was used to obtain the ciphertext. This allows for tighter proofs. So I mentioned that we analyze this also in the quantum random oracle model. So let me quickly review what the quantum random oracle model is. So do we want to analyze the post-quantum security of the schemes? And then we have a random oracle model scheme and the quantum adversary. One should model the fact that an adversary can implement the public hash function, which is modeled as a random oracle, on a quantum computer and then can make superposition queries. So because the adversary can make quantum superposition queries, we should extend the random oracle model to allow for this quantum access. And a common lemma, which then is used in those proofs, is a well-known one-way to hiding lemma, which allows one to reprogram the quantum random oracle model and bound the difference between the original and the reprogrammed one. Next, let's look at the simple, not size-preserving ACVC transform to obtain a worst-case correct scheme, which is in CPA secure. So this is a well-known folklore transformation. What we do is we pick a random ring element, encrypt it using the entry one-way function, and use this random ring element R as a one-time pad with a random oracle F, and XOR it with a message. So because of the second part, it's not size preserving. And the intuition here is then that the correctness is now independent of the message. So even if you pick a worst case message here, because the ring element R, the correctness only depends on the ring element R, which is chosen randomly as part of the randomness. This scheme is worst case correct. So as a theorem, we show that the public key, the original public key encryption scheme is delta average case correct, which means for an honestly generated message. Then it's the transformed scheme is delta worst case correct, which means for adversarially chosen message. So, and then what we also show is then that if the original scheme is one way, then the derived scheme is in CPA secure in the quantum random oracle model. So now that we have derived a worst case correct scheme, we can now apply the Fujisaki-Okamoto transform here to then obtain CCA secure chem and true C. So let's review the Fujisaki-Okamoto transform. So the Fujisaki-Okamoto transform works by de-randomizing the encryption scheme using a hash function G. And then in the decryption, we recover the R prime by decrypting the ciphertext C. And then we re-encrypt, because we de-randomize the scheme, we can re-encrypt this R prime and check against the original ciphertext. And if equality holds, we can return the chem key, H of R prime. And otherwise, we return a error symbol bot. And this is what gives it the chem its CCA security. And it's well known that if you input worst case correct CPA secure public key encryption scheme, that then it yields a CCA secure chem. And so this explicit rejection variant has been proven secure in the quantum random oracle model. And the advantage of it is that it yields a slightly more efficient decapsulation algorithm. Because you don't have to timing side-channelly securely implement this decapsulation. Okay, so now that I've talked a little bit about the last row here and how to obtain the CCA secure chem, let me now come to the maybe a little bit different approach that we use, which is N through A, which is directly worst case correct. So the idea of N through A is to use distribution psi, which is generated the following way. We take B1, B2, B3, B4, uniformly random from the set, and compute B1 plus B2 minus B3 minus B4. And an alternative way of generating this distribution is to compute it the following way here, namely B1 minus 2 times B2 multiplied by B3 and then multiplied by 1 minus 2 times B4. And now everything mod 2, you can actually recover the original B1. And the idea then of N through A is to use the message M as B1 and sample B2, B3, and B4 random. So the adversary then only controls E mod 2 in the N through ciphertext. And we can then show that the worst case decryption errors are about the same as average case errors. And because of that, you don't need an additional error reducing transformation. So this is what the scheme looks like for encryption and decryption. Notice here in line 2 and 3, we do what I said in the slide before. We use the message as B1 and sample B2, B3, B4 uniformly random, and then construct it as a distribution I showed you before. And then we just do the usual N-through encryption. And for decapsulation, for decryption, we then take things mod 2, and also in the private key, instead of multiplying the F prime by 3, we multiply by 2. And what we show is that then, or what you can show then is that the scheme is one-way CPA secure based on the NTRU and ring LWE2 assumption. The ring LWE2 assumption states that it's a variant of ring LWE, which states it's difficult to compute E mod 2 instead of E. So then again, we apply, we have now a scheme which is in worst case correct, and then we can apply FO to obtain a CCA secure kernel. So let me now say a few words about the size preserving ACVC transform. I'm not going to show you the exact scheme, but just say a couple of things about it. So it's similar to the ACVC 0 transform, but in contrast to it, it's size preserving. And to prove it secure and analyze the correctness errors, we need some a little bit different proof techniques. So we use a measure and reprogram theorem, which is a theorem used in the context of proving Fiat-Shamir secure in the quantum random oracle model. And for the worst case error bound, we use the Höfting bound. And for the exact details of this construction, I refer you to the paper. And then again, we apply the FO to obtain a CCA secure KEM. So now let me come to the results and talk a little bit about performance of the final CCA secure schemes, in particular more about CCA N2A. So these are some performance results here for key generation, encapsulation, and decapsulation performed on a Skylake machine. The public key size, the ciphertext size, and the security level. And we compare it to NTRU HRSS 701, to NT-TRU Kyber 512, and Kyber 768. Here the 90s version. So here we instantiate the NTRU-A scheme, the CCA secure scheme with ring dimension 648 and modulus 2917. And we obtain a scheme which is, compared to the other schemes, as efficient as key generation as Kyber 512. Significantly more efficient than NTRU HRSS 701 in encapsulation and decapsulation. And also more efficient than NT-TRU Kyber 512 and Kyber 768. For the public key and ciphertext size, we are more efficient than all the other schemes except for Kyber 512, which is slightly more efficient, more compact in public key size and ciphertext size, but at a different security level. Yeah, and if one thing maybe you can notice is that it's here when we compare to NTRU HRSS 701, it's at a slightly better security level. So it's more efficient at a slightly better security level. Yeah, so that's about it regarding performance and compactness. So to conclude the talk, we showed different ways to obtain worst case correctness for NTRU, proving them secure in the random oracle model and quantum random oracle model, which allows us then, due to the worst case correctness, to apply the Fujisaki-Okamoto transform to obtain CCA security. And by doing our analysis, it allows us to use a smaller modulus Q because we don't need perfect correctness, which leads to a better security and more compact scheme. And when we instantiated our design with NTT-friendly rings, we obtain 3 different efficient CCA secure NTRU designs with flexible parameter choice. So thank you for listening, and that's the end of the talk.
Minute or so for questions. Yes.
Thanks for the talk. In your final CCA security bounds for your three variants.
Yeah.
Do you recall what is the dependence on the worst case error with respect to the number of quantum random oracle queries?
You mean in the random oracle model or in the quantum random oracle model?
Quantum random oracle.
Yeah, so we use the bound, the explicit reject proof by Fair and colleagues. So the bound is, I think, let me not, it's something.
Like square root?
Yeah, square root delta something, but I'm not, it's slightly worse than the implicit reject bound proof because they first apply the one-way to hiding lemma and then do the proof. When you do the FO with the implicit rejection, you first do use the delta correctness and then use one-way to hiding in the last step of the proof. So it's slightly worse than that. But I don't remember the exact bound. But because you have the square root first and then you do your delta correctness, it's slightly worse than that. Yeah. But if you want to instantiate it with the better, you can still always, of course, do the implicit reject variant, and then you'll have the state-of-the-art bound.
I see. Can I ask a follow-up? Or so Hovelmans et al. They had like a result last year at Asia Crypt on how to fail gracefully or something, where they came up with a proof for the explicit rejection, which with better bounds with respect to the correctness error, where you don't have the square root bound.
Yeah.
But then they had many more parameters like a tail bound for errors and things like that.
Yeah.
So did you look into their results for your paper?
So I didn't look into that. So one thing about that work, it's interesting work, but I think it's a bit difficult to concretely instantiate because it's a very different approach. Maybe we can talk about this more offline, but it's not as straightforward, I think. Yeah.
Oh, thank you very much.
Thank you. Thanks for the talk. Thanks. Let's thank Julian again. All right, our next talk is a lightweight identification protocol based on lattices. The work is by Samit Duzlu, Julian Kramer, Thomas Popelman, and Patrick Struck. And Thomas will be giving the talk. And it's paper 99.
Thank you.
Yep.
You're supposed to swallow this. Okay.
So yeah, thank you. Hope you can hear me well. Yeah, so this is a work on a lightweight identification protocol based on lattices. As Chris mentioned, it's a joint work with Samit Duzlu, Julian Kramer, and Patrick Struck from University of Regensburg. I'm with Infineon, and yeah, I would like to give a short motivation for this work. What we're looking at is an identification problem. So there's a verifier, a party that wants to check the identity or authenticity of a party. And then we have a prover, and the prover wants to interact with the verifier and assert that assert its identity. And this is a lot of practical applications, also in an industrial setting. And some practical applications are you want to prevent counterfeit. And counterfeit could be the counterfeit of batteries, chips, machine parts, and obviously such counterfeit could cause great harm. And what we also want to do is we want to do this in an efficient manner, using cryptography, and then of course also using post-quantum cryptography. And when looking at approaches that we know in practice, of course, there are more involved approaches in theory. Then what we usually take is, at the moment, we either use a symmetric key, so the verifier encrypts the nonce, the prover decrypts the nonce and sends back the nonce. We use public key encryption, so we encrypt the nonce, the prover decrypts the nonce and sends back the nonce, or we use a digital signature, and there the verifier just sends the nonce, the prover decrypts, signs the nonce and sends back the signature. And this is kind of the toolkit that we have available today. And what's used in practice, I think, mostly are digital signatures, but also sometimes public key encryption or schemes based on Diffie-Hellman. And when looking into this, if we want to move this into a post-quantum setting, then it's clear we want active security, because usually you can assume there's a man in the middle that is tampering with the identification protocol. And we want protection against physical attacks, because an attacker could try to extract secret keys or secret information from a prover and then use this, for example, to build counterfeit devices. And we want an asymmetric scheme because we only want a secret in the prover, because otherwise we would also have to protect the secret in the verifier. And I think what's quite interesting is on a very high level that things are now a bit different with PQC and with the recent decisions by NIST for standardization. Because when looking at pre-quantum schemes, then usually ECC signatures and Diffie-Hellman roughly cost the same, and the physical protection is well understood. So when you implement such a scheme, or when you design a protocol or choose a protocol, it doesn't matter that much. There are some considerations how you want to move your scalar multiplications. If you want to also get a secret key out of the identification protocol. But I think in practice, a lot of the available schemes that we see to protect against counterfeit, they use just elliptic curve digital signature scheme, because it's well understood. But the change now is with PQC schemes is that signatures are getting much more expensive. So when looking at Kyber versus dilithium, then the dilithium signature is much slower. It's also much larger. So this kind of we don't care what we use doesn't work anymore, and we pay more for signatures. But then also we could of course say, okay, let's not use a signature scheme. Let's just use a lattice-based public key encryption scheme or a CAM. And there the cost is there we see that it's very expensive to protect the current schemes against side channel attacks because of properties of the Fujisaki-Okamoto transform. So the Fujisaki-Okamoto transform, we've seen this already in previous talks. It requires you to perform a re-encryption scheme to check that the ciphertext was honestly generated. But this is also a plain text checking oracle that can be used by side channel attacks to break the scheme very easily. And this is a really severe attack, because usually when you think about side channel attacks, you just think, okay, I have to do some DPA, some SPA, something like that to extract a secret key. But in this attack on the Fujisaki-Okamoto transform, you basically just have to check if a computation of a large computation was different, if something changed. Because if you decrypt a different cipher, if you send malicious ciphertext, you do a decryption, you get a different randomness out. And then when one bit of this randomness changes, the whole decryption, the whole re-encryption changes. And if you can detect this, you can attack the scheme. And this is very hard to protect against, and a very severe attack. And there are a lot of works that are trying to protect the FO transform against side channel attacks. But if you do this, it gets expensive. So what we are looking at then is how can we maybe mitigate this impact a bit. And we just look at the naive construction, just using a public key encryption scheme. So usual setting, the verifier has a public key. This has been authenticated already. We have the prover with the secret key, and then we have a challenge computation. So you choose a random message. The random message is encrypted with the public key. There's the challenge. The challenge is sent over to the prover, and then the prover is just decrypting it using a secret key and the ciphertext, and then sends over the message. And in the end, the verifier compares if the message matches the message that was sent over. If we would instantiate this with Kyber here, then we would have the issue with side channel attacks on the FO transform. If we would just instantiate it with a CPA in CPA secure Kyber, of course, then we wouldn't have a security against malicious ciphertext attacks. So what can we do? And when looking at this, why do we have the FO transform? As said, the goal is to check that the ciphertext was honestly generated. And maybe we can find a different way to check that the ciphertext was honestly generated. And then what we also see is that the in CPA secured decryption of Kyber is quite fast and straightforward to protect. Because it's fast, we also have a lot of kind of cycles left or time left to apply protection measures. It's mostly arithmetic, so there are not that many nasty operations. But the re-encryption, as said, is also really nasty, and this is also a problem. It's a long operation. it works on secret dependent data, and then also we have to mask, or we have to somehow protect binomial sampling, hashing, mask comparison. So a lot of operations that are really nonlinear and that are ugly. Usually, at least the beauty of elliptic curves is that you have a lot of structure, a lot of arithmetic structure you can use to protect the schemes, while in the lattice-based CAMs, we have a lot of arithmetic, then some hashing, nonlinear operations, arithmetic again, and then building nice protection schemes on top of that is very hard because you're crossing these boundaries a lot. And in our construction, we now move from a 2-pass protocol to a 4-pass protocol. And what we're doing is we use the normal challenge computation using an encryption scheme. So we are sampling some randomness. Then we use this randomness to extract a message and some random coins for the encryption. And then we feed in the public key, the message, and the coins into the encryption scheme. We send over the ciphertext, and then we have this usual response computation. So we store the ciphertext, we decrypt the message, and then instead of sending back the message already, we are sampling a random value. And we're putting the random value and the message into a hash function, and we derive a value h, and we send over this h to the verifier. So the prover decrypts the challenge and commits to the response, but it doesn't provide it. So at this point in time, if the prover has sent a malicious ciphertext, okay, well, we have decrypted it. We know how to protect this decryption, but you can't learn anything from this H here right now. And what we then do is, what the prover is then doing, the prover is, the verifier is then opening up its randomness, so it's sending over the lambda, and this allows the challenge verification to recompute the ciphertext. And with this recomputation, we can check that the ciphertext was honestly generated. And this then afterwards we compare the ciphertext we've computed during challenge verification with the ciphertext we've received at the start of the protocol. And if they don't match, we are not returning anything because we don't want to reveal information that depend on the secret key. Otherwise, we could either return the message itself. What we're doing here is we are returning just the randomness, and then during response verification, the verifier can just also do this computation of the hash with the randomness, the message, and check if the computed H prime matches the H that was sent over before. And then the question is this really is this something that works well? And for this we did an implementation based on Kyber. We have different experiments and different implementations, because for an implementation, of course, we could use either the reference code or something more optimized, and we've done both. So our implementation is done on ARM Cortex-M4 using either Pico Clean or Pico M4 with the M4 F-Speed variant. So the Cortex-M4, this is a microcontroller that is very common. It's also the reference platform that NIST designated as the platform for the evaluation of post-quantum cryptography on an embedded device. This could be small microcontroller controlling some machine. It could also be a smart card or an authentication chip that is preventing counterfeit. Of course, there are also different microcontrollers with different properties, but I would argue that this gives a good baseline indication about the performance of the scheme. What we are used to instantiate is Kyber 768, so the kind of NIST level 3 scheme for measurement. One word of caution, so we are comparing here non-masked versus masked implementations, but in practice this is not sufficient. So there are also other attacks, fault attack, templates attacks. So I wouldn't argue that this is a secure implementation. I just would argue that this is a masked implementation or masked at a certain order. For a secure implementation, in the sense that it's protected against all attacks that are usually in scope, you would have to do a bit more. But of course, this would also skew the evaluation. And then when looking at these implementations, you can see that our protocol on a Cortex M4, and just using Kyber in CCA as an ID scheme doesn't really change much. So there's not really much savings. Some savings I think are here because we use less hashing. But on the other hand, we are also moving from a 2-path to a 4-path protocol, which itself is also a downside. So if you're not considering side channel attacks, then you're probably well off using just Kyber, the classical Kyber in CCA. This is also some data. Why is dilithium expensive? So these are the cycle counts for the prover and the verifier, and here you can see that it's almost a factor of 10 more expensive for the prover to compute a signature. And then, of course, we could use the Kyber 768 CPA secured scheme, but yeah, as said, it's not secure. It's really fast, but again, yeah, there's the time for the re-encryption is missing. Now the question is, how does it work, or what's the advantage when looking into side channel protection? What we've done is we've implemented the scheme as said with no protection, and then also with an open source implementation that can do based on an open source implementation of Kyber 768 that is protected to the first order. And then we also use, we extrapolate the cycle counts from a published implementation where the source code is not available to get some data for the second and third order. These are then approximate speed ups. But of course, in practice, I wouldn't chase the last 100 cycles when looking at this. So this is just to give a rough overview on the performance. And what we can see is when we compare our protocol to a masked first order Kyber 768, then we can already see a speed of roughly 3. And this is exactly due to the performance hit for Kyber. This is due to the cost for masking the re-encryption. We of course also have to protect our secret key decryption operation, as Kyber also has to do, but as said, this is much cheaper. And then when going to higher orders, the speed up becomes even larger. So when looking into second order masking, then we have a speed up of roughly 8.5, and then third order 9 point something. So a significant speed up. And yeah, this is basically due to the fact that in our scheme, there's just less code that we have to protect, while in the classical Kyber, there's much more to protect. And then, yeah, in conclusion, what we did, we gave an approach to use Kyber in an ID authentication protocol in a practical setting. There are, of course, interesting trade-offs involved, because is it worth to move from a 2-pass to a 4-pass protocol just to save maybe cost for side channel hardening? This is open, and this, of course, depends also on other maybe system considerations, how complex it is. And then also the next question is maybe this move to a 4-pass is not necessary if the community is getting better in protecting instantiations of Kyber against side channel attacks. Of course, it could be worthwhile if the community is also getting better in providing attacks against Kyber. So it really depends on this comparison and the savings that you can achieve. And yeah, with this, I would like to refer to the details in the paper. There's also a bit of advertisement here for a personal project, which is a GPT-2 based paper abstract generator trained on ePrint. Try it out if you want to, but it's tech from like ancient tech with the recent advances. But anyways, and yeah, with this, thank you for your attention, and I'm happy to answer questions.
So we have a few minutes for questions. I have a question. So the 4-pass protocol that you have, what's the connection, or is there any relationship between the structure of that protocol and the Hopper-Blum or Jules-Weiss, if you're familiar with these? Those are based on learning parity with noise, and they have, I think they're also 4-pass. So I'm interested if you have any.
Unfortunately, I'm not qualified to comment on that.
Other questions?
Hello, I have a question. So if we reduce the protocol from 4-pass to 3 paths, for example. So what will happen? For example, if we just erase the last round, what will happen? Yeah, I just curious about this question.
So you mean if we would just not do this,
Yes, for example.
then the verifier wouldn't get any assurance about the identity or authenticity of this part.
So it can achieve single party authentication. And is there any security issues that?
But I think you learn nothing in the end if you would do that. What would we gain?
Yeah, since I think from 2 paths to 4 paths is you enhance the round complexity, so maybe more secure. I'm not sure. Yeah.
Yeah, of course. If we can remove one of the passes, I think that would help. I mean, would be interesting to see if this is possible. I don't know.
Okay, I know. Okay, thank you.
Thank you.
Any other questions? Good, we're at time. So let's thank Thomas again. So our last talk of the session is entitled Polka Towards Leakage Resistant Post-Quantum CCA Secure Public Key Encryption. And the paper is by Clément Hoffman, Benoit Libert, Charles Momin, Thomas Peters, and François-Xavier Standard. And Clément is the speaker. It's number 94. Do we have it? Oh, great. All right, the floor is yours.
Hello, everyone. So thank you for attending this last talk for this session. This talk will be about basically designing a CCA encryption scheme, lattice-based, that is efficient to protect against side channel attacks. So what's going on with post-quantum cryptography and side channel attacks? You might have seen there have been plenty of attacks, sometimes against lattice-based schemes, sometimes against number theoretic transform, against Fujiseki Okamoto transform. And the outline is the countermeasures are expensive. And this is because those schemes were not designed with side channel attacks in the first place. Like it was not taken into account when designing the scheme. So a little bit of background with side channel attacks. I don't know if you're all familiar with that, but most of the time we're working in a black box framework. We consider the algorithm is a black box, and adversary can only see the input, the output. But if at some point you want to implement your scheme and you want it to run in real life, it will run on a physical device, like a physical processor. And it means that this processor will have some physical emissions, like for instance, its power consumption, its electromagnetic fields, that an adversary will be able to exploit to have information about some values that are handled by the processor. So basically, we can consider that an adversary gets some information about every intermediate values, and if at some point he gets enough information, he can get back this value, let's say it's a secret key, for instance. We do not need to get into too much detail, but let's just highlight that there are some different levels of side channel attacks. So some categories are, for instance, a simple power analysis. This one can be used basically anywhere. It only requires a few traces, so it can target some ephemeral secrets, but it's not too powerful, so it's not too expensive to protect against. Differential power analysis, for instance, on the contrary, they require a large amount of traces, so they can only target long-term secrets that will be used in many executions. But since they are more powerful, it's more expensive to protect against them. If we look at what happened with symmetric crypto, 20 years ago, at the beginning of side channel attacks, people took the schemes they had, so basically AES, and said, okay, how can we make this protected against side channel? And the answer was we need the strong attacks apply everywhere because IS was not made to be secured against side channel attacks. So the strong attacks applied everywhere. The solution was to have strong countermeasure everywhere, which is expensive. Nowadays, we can have some schemes that where the strong countermeasure only needs to be on one part of the scheme and the other, so the green part, only requires some lighter countermeasures. And this is basically the kind of result we want to have for post-quantum cryptography. We want to design a scheme that will be a little bit less efficient than the standard, let's say Kyber, for instance, in an unprotected implementation, but which will be cheaper to protect and which will become more efficient with security against side channel going up. So leveling approach can be, you can have a huge factor of gain because the more secured you want your implementation, so bigger the gain will be. Let's start with an example. So it was already introduced in the previous talk. So we have the same issue with FO transform. Basically, FO transform is used to grant the CCA property from a CPA scheme. It does that by re-encrypting. After your decryption, you re-encrypt the plain text you got in order to check that if the ciphertext was valid. So in a black box framework, it rejects the invalid ciphertext, preventing an adversary to get information with this. But in a side channel framework, you can do so that the plain text, which is the output of the CPA decryption, is super key dependent. Let's say it's 1 bit of the key to make it simple. And then this 1 bit of the key will be re-encrypted. So you just have to distinguish if this bit was 0 or if this bit was 1. So this is like extremely easy. So it leads to an attack that is super powerful, so super expensive to protect against. So this is a feature you don't really want against such an attack. If you're able to design your scheme with that in mind in the first place, you will try to avoid the Fujiseki Okamoto transform. So what we provide is a CCA lattice-based encryption scheme that relies on a classical assumption, RLWE, that is relatively efficient, the same order of magnitude as Kyber, and that is proven secured in the classical models. Our main contribution is that it is much cheaper to protect against side channel attacks. And we get that with several tricks that I will present. So getting rid of the FO transform, using some tricks to randomize the intermediate values, and so on and so on. So the outline of the scheme is it's a classic LPR-based scheme. So you have RLWE ciphertext, classical, with A and B being the public key, the errors, the random coins being small. And you use this to derive a symmetric key and to perform an authenticated encryption scheme, for instance, ASCON. So this is our encryption. In order to decrypt this, we need to be able to retrieve the symmetric key. So basically, we need, in the post-quantum part, we need to be able to retrieve one of the error. From this error, we will be able to get all the random coins and then decrypt. For the rest of the presentation, I will only focus on the decryption. Why is the decryption? Because it's the operations that use the long-term secret. And in the first time, we only consider the security for the long-term secret against side channel attack. So it's a little bit disappointing. We also want message confidentiality, but you have to start somewhere. How do you decrypt? You introduce an intermediate modulus. So it's a value that is bigger than the coefficient of the error, but it's still smaller than the modulus. With this intermediate modulus and your public keys that are built a good way, you can get back E2, then R, then E1. When you get back those values, you check their norms. And with that, you can see if they are small and if the ciphertext was valid in the first place. But when you do that, you do explicit rejection. You check the norms. If it's too big, then you reject. You don't need to re-encrypt as in FO. Note that this needs to be combined with the symmetric part. You cannot use like only this part as key encapsulation mechanism. If you do that, it won't be CCA. Okay, so now we got rid of the distinguishing attack that was super powerful, super expensive to protect against, but we still see here a DPA attack path because we perform directly a multiplication between the secret key and the ciphertext, a ciphertext that can be controlled by the adversary in the CCA game. So now we want to get rid of that. For that, we use the homomorphic additivity of RLWE. The idea is that we can randomize the ciphertext. We generate dummy ciphertexts that are just generated as the regular ones. We sum the regular and the dummies. So we get new ciphertexts that are totally randoms because the dummy ciphertexts are random. Then we perform all of our decryption with those new ciphertexts. And in the end, we are able to retrieve the random coins we needed and to decrypt. Note that with those new ciphertexts, we can introduce a new check norms, which with a different bounds because of the addition, the norm will be a bit bigger, but this will still be able to reject the invalid ciphertext. And what we did here can seem absurd in a black box framework because we only added operation like some intermediate steps to get to the same values. But what it means from a side channel perspective is that the adversary cannot control the ciphertext anymore. So all the values that are, all the operations that are happening after the multiplication with the secret key are now random. And so they are not DPA attack path anymore. So if we look at Polka with this figure, we classified all the operation with the level of security we need to grant. So basically the left part, the green one, is only weak against simple power analysis and needs light countermeasure. And we managed to only have one operation on the post-quantum parts that needed to be protected against TPA. There's also the symmetric parts that need to be masked, but we can hope that symmetric guys provide efficient hash function and efficient authenticated encryption schemes. Then we still want the black box security. I mean, there's no point in having side channel security if your scheme can be broken without side channel. So the proofs and CCNS come, as we discussed, from the rigidity property and explicit rejection. The quantum random oracle model proof has to be reduced to implicit rejection and not rejection, and then it's non-result. And we can use some non-results. What's interesting is that all the tweaks I presented are part of the scheme, and they need to be taken into account when performing the black box security. It's not you have a scheme without the tweaks, you prove it CCA, then you add the tweaks on it. You have to make sure that those tweaks do not create any vulnerabilities. The last tweak we used is a bit more complicated. I will go fast on this one, but the idea is that when you perform your multiplication with the secret key, it appears to be hard for an adversary considering the leakage of this output to get back to the secret key. It's kind of a learning problem because what we say is, what is the output of this multiplication? It's just the multiplication, and the adversary only has the leakage on it. So the leakage can be seen as a rounding function. So the rounding function here won't be discarding the less significant bits, but it will be, for instance, the Hamming weight, which is a classical model for the leakage function. Those things have not be proven secured, like with a reduction to LW yet. They have been studied, and we look at some algebraic properties that's shown, say, appear hard for some leakage model like the Hamming weight. This trick is a little bit more heuristic. Even if it does not work, all the previous results hold. This one only makes things easier to be masked. So what we want now is to provide a concrete implementation so that we can really compare in unprotected implementation and protected implementation against the standard, for instance, Kyber. We also want the message confidentiality against side channel attacks. It's great to protect the long-term secrets, but it's not all we want. And also for the last part, we want to have some proofs for those hard physical learning problems. And we want to consider them against some physical assumption. To conclude, I just show this figure. That is the expected gain you want. And basically what we have to understand is even if the scheme is probably a little bit less efficient than Kyber, at some point, if you want to implement it in a secure way, it will become more efficient because it's cheaper to protect. Thank you for your attention. Do you have any question? I was way too fast.
Not too fast, but we do have a few minutes for questions. I have a question. So I'm interested in this learning with physical rounding question. So is there a realistic model for what the noise looks like that the adversary sees or that the noise is introduced?
This is a good question. The model is always a big question. Basically, you can have some complex models that are close to the reality, but hard to analyze. So what's at the moment, on the papers that were published on this, the model is just an adversary has access to the Hamming weight of the output without noise. In real life, an adversary will never get the Hamming weight directly. It will have noise on it. Probably that the noise makes it a Gaussian noise. Probably that the noise makes the problem harder, but it's also harder to analyze. So even without the noise, problems appears to be hard. There is a follow-up work that will be published at Crypto that generalize this model to linear and quadratic leakage model. So it's like the Hamming weight, but you have coefficient in front of your different bits. Some bits weight more in the leakage than others. And in the end, you have the same hardness properties than before.
So on a high level, is there some way that your technique for using the homomorphic properties of the crypto system, does that generalize to any like randomizable crypto system? Can you show that if a crypto system is randomizable, then DPA is as hard as SPA?
It's not, there is not a strict equivalence. It's not like if there are some ephemeral values, you only have SPA, and if there are some long-term secret, you only have DPA. Because in post-quantum cryptography, sometimes even in one execution, you have many and many traces, many point of interest because the operations are heavy, and you end up being able to perform DPA with a single trace. But this idea makes things harder for sure. And this is, at first, what we try to achieve is like just take the implementation and find some ideas to make things harder without yet being able to prove that it will be hard enough in the probing model, for instance, or things like that.
So did I understand you correctly? You were only able to prove it specifically for under RLWE, but you think it works in general?
If you can randomize the value, it will always be harder. How much harder? It is hard to prove, but it for sure will be harder. And all the attacks that are used most of the time won't apply. So probably that it works in general.
Any other questions? So we'll wrap up. Let's thank Clément and all the speakers from the session. And we'll resume at 11 o'clock, which is in 22 minutes.